In this video, we're going to introduce some key terms that we're going to use a lot in special relativity just to make sure that everyone's starting out on the same page and that everyone knows exactly what we mean precisely when we use certain words. So the first is when we talk about events in special relativity. Whenever I use the term event, I'm talking about some physical occurrence. Often we want to think about it as a physical occurrence that occurs at a particular location at a particular time. And generally, we want it to be, um, we like to think of it as something that's sort of maybe relatively small and occurs over a relatively small amount of time. So, for instance, a concert on everyday language, you might say a concert is an event, but it lasts several hours. When we talk about events in special relativity, you want it to be something that, I snapped my fingers. That was an event. I snapped my fingers. It occurred sort of in a small amount of space. I mean, of course, my hand has some finite size, but we want to think about it as occurring at a point in space. So we want it to be relatively small and we want it to last for a very short amount of time, right? We can think about the instant right when the snap sound is made as being the event, and right where my hand is vibrating to make that sound. That's the location of the snap. So an event is something that happens at a point in space at an instant of time. So for instance, a snap of the fingers. Or two particles colliding, right? Two particles are going to collide at a particular instant of time in a particular very small amount of space, right? An instant. So this is going to be very important. Space-time is a space where, an abstract space, where we have our spatial dimensions along with our dimension of time. So we know in special relativity, time and space are no longer sort of these totally separate things. In classical physics, you think we live in this three-dimensional world, and then time marches on, and we often parameterize things by time. We say, oh, this object is moving with this trajectory as a function of time. We're going to want to think of things really differently in special relativity. And the reason is because it's a smart thing to do. It's going to be a convenient thing to do because space and time are no longer as separate as they used to be because of things like time dilation and length contraction, and ultimately the Lorentz transformations. We're going to explicitly see this mixing of space and time. And now we're going to want to think about time instead of as this separate thing that we parameterize things by. Instead, we want to think about time more like just as a fourth spatial dimension, assuming we're living in a three-dimensional world with three spatial dimensions. Time is going to be, we're going to treat it a little bit differently. But in general, you want to think about it just like you think about space. It's just going to be a different dimension. And in particular, we're going to draw a lot of space-time diagrams, which look like this generally. So I can only draw two dimensions. I can't draw four. I can't even draw three. I mean, you could sort of try to draw three dimensions, but it's hard, right? So generally, we'll just draw two, and we'll want to pick one as a spatial direction. Usually we'll think of this as X, and then one as time. And notice that I'm putting time along the vertical, which is the conventional norm in special relativity, to put time along the vertical and X along the horizontal, which might be different from what you've done in the past. Often we draw the diagram the other way. So it's very important to keep this in mind. We're drawing time along the vertical. This is known as our space-time diagram. One fact about these is that if we set the speed of light equal to 1, which is what we'll usually do, then 45-degree lines on our space-time diagram represent the world line of an object moving at the speed of light. So these 45-degree lines are representing the way in which light would travel through the space-time diagram. And that's going to be a very helpful fact when we're drawing these diagrams. So with these diagrams, we can have a space-time coordinate. So now that we're living in this thing called space-time instead of just normal space, an event is going to occur at a space-time coordinate. And so rather than writing this a normal three-dimensional, three-spatial coordinate as x, y, z, we have t for time, x, y, and z. So whenever we label an event, we label it by our 4 space-time coordinates, times time, and then our 3 spatial coordinates. On our space-time diagrams, it'll be helpful to draw things known as world lines, which represent the paths of particles through space-time, or the paths of objects, I should say. So if we draw another space-time diagram, we can draw different sorts of objects. A point in our diagram might represent event A, which occurs maybe at time TA, XA, YA, ZA. And then we can also draw on it a world line, which maybe just looks like this, which is the path that maybe some object is moving. So this object is moving around in space. It looks like it's sort of moving back and forth along the x-axis, and time is marching forward, right? So it's moving forward in time and in space. So that's what I mean when I'm talking about the world line. I should label that. This is a world line of some object. Events are at points, world lines are lines through space-time. It's going to be very useful to calculate something known as the space-time interval. We write this as delta S squared, although don't take that squared too literally. This is really, you should think of this sort of as a symbol representing the space-time interval. The reason I say that is because the space-time interval can actually be positive or negative, because we calculate it as the change in time, perhaps between two events. This is like the interval between, often we think of this as between two events, minus delta x squared, minus delta y squared, minus delta z squared, where of course my deltas here are representing the change in time, the change in position, etc. Change in the x coordinate, change in y coordinate. So this thing can be positive or negative. So that's what I mean by don't take the delta s squared too literally in the way that you're used to. One thing I also want to mention right here is there is a sign convention that changes often depending on what field you are thinking or you're working. So this convention where we have minus signs attached to all our spatial coordinates, this is common in particle physics. In general relativity textbooks, often delta S squared is defined as minus delta T squared plus delta X squared plus delta Y squared plus delta Z squared. That's just a different convention that is more common in the general relativity world, in general relativity literature. So, because here we're doing particle physics, we're sticking to the more particle physics convention where they attach the minus signs to the spatial coordinates when we calculate our space-time interval. You might be wondering, why do we care about such an object? It seems kind of like a weird object. This object is going to be invariant when you change to different reference frames. So delta S squared is the same in all inertial reference frames, which means it's going to be a very handy tool for us. The fact that if I calculate the space-time interval between two events when I'm sitting here in my office, and then if you calculate it, you're riding by in your car and you see those two events and you calculate the space-time interval and you get the same answer, that's something that we can utilize because we already know in special relativity, if I just calculate the time between those two events, if you're going by on a car, the time between the two events you calculate is going to be different because of time dilation. Similarly, if I calculate the distance between these two events and you're riding by in your car, the distance you're going to measure will also be different. So time is different, distance is different, so it's going to be hard for us to talk. But if I use the time that I measure and the distance that I measure and I plug them into the space-time interval calculation, the number I get will be the same as the number that you get when you're driving by in the car. So this is going to be a really useful way for us to talk to each other when we're in different reference frames. So the space-time interval is an incredibly helpful and an incredibly important quantity. There's another reason it's useful. So this interval, so I already mentioned not to take this delta S squared thing, the squared part, too seriously. This is something that's not really being squared in the normal sense. It can be positive or negative. And we have different terms for if the space-time interval is positive or negative or zero. So the space-time interval can be one of three things. It can be said to be time-like, which is when delta S squared is greater than zero. And that again is with our particle physics sign convention, and general relativity, time-like is the opposite. So be careful if you're reading other resources. It could also be light-like. This is when the space-time interval is exactly equal to zero, or it can be space-like when delta S squared is negative, it's less than zero. The way I think about these terms is that time-like, so if this is representing the motion of some object, time-like means that object has sort of moved more through time than through space. Right? Delta t squared is bigger than delta s squared, x squared plus delta y squared plus delta z squared. So it's sort of moving more in time. The delta t is bigger. On the opposite end of the spectrum, space-like means the separation is more through space than time. Right now, delta x squared plus delta y squared plus delta z squared is greater than delta t squared. And of course, light-like, if this is representing the motion of some particle, a light-like particle must be moving at the speed of light. So at the speed of light. Or if this represents the interval between two events, then a signal between those two events would have to move at the speed of light in order to get from those two events. So these terms are very useful if we want to think about causality. So let's draw a space-time diagram. We have X and we have T. And we'll draw on our 45-degree lines. And let's put event A right at our origin. Event A is something that occurs. So I turn on a light, right? That's something that I can do that is at a time and at a location in space. If I want to think about all the other events that causally led up to me turning on that event, that light. So for instance, in order for me to turn the light on, I have to first stand up and walk over to the light switch and then reach out my hand and turn it on. So there's like a chain of causality there. All of the events of me standing up and reaching out my hand, all of the events that caused me turning on the light must exist down here in what's known as the causal past of A. An event over here, if that blue dot represents me standing up from my chair and my light switch is over at event A, I would have to move faster than the speed of light to go from that blue dot to event A. I would have to travel on a space-like trajectory, which is not allowed, right? It's not we know that we cannot move faster than the speed of light. So I'd have to move faster than the speed of light in order to get from that blue point to event A. So the blue point is not in the causal past of A, because nothing that happens at points like that blue point, which are space-like separated from A, can cause A. We can also consider the causal future of A, which is to say, what are all of the things that happen in the future that could potentially be causally related to A? Maybe they aren't. There are lots of things that are going to happen in the future of A that are not directly caused by A. But what are all of the things that potentially could have been caused by event A? Those all live in the causal future. Because if I look at this other blue dot over here, again, any signal would have to move faster than the speed of light to get from that point A to that other blue point in the future of A. And so these blue points again, this is, this blue point is space-like separated from A, and therefore they cannot have any causal relationship. Same with this other blue point. So both of these, this one and this one, they're space-like separated. On the other hand, all of the points in the causal past and causal future of A are time-like related. There's a time-like separation between these. And so those can be causally related. So that's a big reason why these terms are going to be very helpful terms for us to use. Okay, so those are a lot of the key terms that will be coming up in discussing special relativity.